Today we're going to start with a short presentation around transformation parameters and then development of models to move between old datums and new datums, or looking at deformation as well. So I've got some examples that talk about when you do a transformation from one datum to another datum, there's an easy way to do it and there's a harder way to do it. And I'll talk you through the different examples. The harder way sometimes means it's a little bit more accurate, but it's a lot of extra effort. So we'll talk about these kind of options. For those of you who joined our impromptu session at lunchtime yesterday, this covers some of what we talked about in that session in a little bit more detail. And then we'll have some time for discussions and for questions at the end as well. So let's get started. So we're looking at the differences here in different types of reference frames. So if you have a look at that image on the right-hand side, you can see that those three axes, if you look at where those three axes join, that's the center of your reference frame. So that's 0, 0, 0 for X, Y, and Z. And then the other one, the blue one, might be your old reference frame. So you're trying to move from the blue one across to the black one. And then in between those, there's a change in where the center of the reference frame. That's the translation component. That's the change in X, Y, and Z between the two reference frames. And then you can also see that the axes rotate. So you can rotate each axis as well. So there's 3 translation, 3 rotation, and then there's the scale, which is the size of the reference frame. So that's where our 7 parameters come from. And the reason that we want to change these, it's different in different countries. Sometimes it's due to earth dynamics, and I'll show you an example of New Zealand, where they have a lot of earthquake activity. So they're not updating their reference frame out of need or out of desire, or to be just to be accurate. They have to go through this process because the earthquake has moved property boundaries and people want to know what they own and where it is. And I think that's a very good reason to be able to go to government and explain why we need to develop high accuracy deformation models. But so you need to be thinking about this in the context of your country. What sort of transformation do I need and how accurate does it need to be for my users? So again, this comes back to the discussion in our roadmap yesterday. Those first 5 steps are all about the communication, the why, and the governance. I know us as technical people, we like to start getting into the details of developing parameters and things like that. But we need to be talking to our users and getting government support before we do anything else. All right, here's the maths for those of you who like the maths. So this is showing you those rotations, the translations, and the scale that I described in the image on the right-hand side. And what you can see is that to develop those transformation parameters, what we need to know the coordinates in the new system that you want, which might be ITRF, some type of ITRF, let's say 2020. And then the original coordinates are on the right-hand side. So that's the X, Y, Zs of the points in the original datum and the X, Y, Zs in the new datum. And then you can solve for those parameters in the middle of the translation, the scale, and the rotation. And in our model, just to bring all this together, you can see that this is the blue circle in the middle with the that says transformation parameters. That's a model that we're trying to develop to allow you to connect your old static datum to your new static datum. And this is what it looks like diagrammatically. How do we go through this process of computing the transformation parameters? You need to know the X, Y, Z coordinates of the same point in 2 different reference systems. So here are the red markers are the coordinates you have for your survey control in your old datum, and the blue ones might be markers where you've observed data in your new datum. And you need to make sure that you have a good number. We'll talk about what good is a bit later on, but a sufficient number of those where you have information in both reference frames on the same ground point. Now, you might be thinking, well, all our data is stored in latitude, longitude, and ellipsoidal height. That's not a big problem. I keep saying we've got to do this transformation parameter work at the X, Y, and Z level. Those Earth-centered Cartesian coordinates, as I refer to it, the center of the reference frame at the center of the mass of the Earth, to get from latitude, longitude, and ellipsoidal height to those Earth-centered Cartesian coordinates, there's a very simple mathematical process you can use to change your coordinates from one coordinate system into the other. So if all your data is stored in latitude, longitude, and ellipsoidal height, you can apply this simple equation, get them into Earth-centered Cartesian, then you can develop your transformation parameters. And then once you have that, it allows you to produce your coordinates in latitude, longitude, and ellipsoidal height, which is what most users want in your new coordinate system. Sometimes there's a need to have a deformation model or a distortion model. And that might be because you might go through the process of applying this transformation in your country. Let's say you use between 50 and 100 points around your country to develop this transformation model between the two systems. Once you remove that distortion, remove that transformal component of the transformation, you might see that there's still differences between the coordinate sets. And as I said, in places like New Zealand, that happens because they get a lot of localized movements of the Earth due to things like earthquakes. Now, you may not even know where that deformation is in your country at the moment. So you may not be in a position to develop this type of deformation model. And I wouldn't suggest that you need to go down that effort to start with, but I want to show you how you could then add to this type of transformation in the future using something like a deformation model or a distortion model. So here's an example of what deformation or distortion looks like on a one-dimensional level, and this is with respect to height. So you can see here throughout, this is the Fennoscandia region, they call it, through Finland, Norway, and Sweden. You can see that the red part in the middle is showing you where the land is lifting up. So if you look at the time series on the right-hand side, you can see that the land is lifting up over time. And this is the scale on the left is showing between -8 and about +8 deformation in centimeters. So 16 centimeters over about 20 years, which is about 7 millimeters per year that the land is rising. And this has been caused by what they call post-glacial rebound. So many, many years ago, there was a lot of ice that was sitting on this land. And slowly, as that ice has melted, the land is rising again because underneath it's called viscoelastic response. You think about pushing, you had a sponge sitting in water and you push the sponge down and it'll bounce back quite quickly. But if you put a sponge in like a bowl of honey, you push it down, you can imagine it'll slowly rise back up. It's because inside the Earth, it's a bit more viscous. So it's sort of holding onto the continental plate, but then slowly it will rise back up again as you release that load on top of it. And that's kind of what's happening in this region. So they need to account for that movement of the Earth rising over time. Australia has a different approach. We don't have post-glacial rebound. We don't have the land rising, but we have the land moving very quickly to the northeast. So you can see from the vectors here that Australia is moving at about 7 centimeters per year. So we need to handle that horizontal motion, which is happening over time, to make sure that the GPS users can work in real time, but then transform back to something like a static datum, so that the traditional surveyors don't need to worry about that Earth movement, that plate movement, which is happening over time. So we did a study to work out what would be the best way to do this plate motion model to detect this deformation over time, or this movement of the Australian plate. And we worked out that we can estimate that the Australian plate is moving almost together. which is very different to the New Zealand method that I'll show you in a moment. And the motion of the continent can be modeled by a sort of a clockwise northeast rotation of about 7 centimeters per year. So this Australian plate motion model was created through the analysis using the APREF solution. So this is an example where you can develop a national model using the high density GNSS data that you have across your country. If we didn't have all the APREF data, we could have used the global model. And the global model fits quite well to the model that we've developed, but the one that we have is more accurate because there was more data that was used to create it. So here's an example of what the change that we went through, to give you an example from Australia. So we had a datum which was the geocentric datum of Australia in 1994, and it was based on ITRF 1992 on the 1st of January 1994 as our reference epoch. If you compare that with ITRF 1992 at 1995, so 1 year on, you can see that the coordinates have moved by 7 centimeters per year to the northeast. And then over time, there were many updates to the ITRF. We had ITRF 94, 96, 97, 2000, 2005, 2008, and then 2014, and now we have 2020. And with each update to the ITRF, let me come back. The reason that they did an update to each ITRF is because someone from the SLR or the VLBI or the GNSS or the Doris community was able to convince the members of the International Association of Geodesy that something has changed in the way that we collect data or analyze data, and we think we can come up with a better determination of what the model of the Earth looks like. We think our data is now better, or our analysis is better, and we want to improve the definition of the reference frame. So that's why they all come at different times. It's not consistent because they wait until they feel like they've got enough evidence to go through the effort to reprocess all the data and create a new ITRF. So when Australia started going through the process for this, which was in about 2017, the most up-to-date realization of ITRF that was available was ITRF 2014. So we decided we were going to fix our reference epoch at 2020. And who can think why we chose 2020 instead of choosing 2016 or 2017? Any hands? Yeah.
Well, I want to believe because it's the most recent realization, so it's better, it's more enhanced for you. Thank you.
Yes. So more stations have come on board, and it's the most recent realization. And then we chose an epoch. We chose 2020 as the reference epoch because we wanted to catch up. We wanted the Australian plate to catch up to 2020. So between 2017 and 2020, the accuracy or the difference between GPS coordinates and Australian datum coordinates would slowly be getting better up until 2020. They'd be coming closer, and then we would be moving away from it. So the users, from a way of updating the coordinate set, the users were seeing things were getting better in the first few years of adopting it. Now it's 2025, we're getting away from it. So, but we've convinced them to move. So that was the first step. So it's part of a marketing communications exercise as well, thinking about accuracy for users. And importantly, as I'll keep mentioning this, there was a big change in the heights between ITRF 1992 and ITRF 2014. As I mentioned, we continued to improve how good our determination of the Earth was. So we were seeing an improvement in our height system in Australia as well. So we developed a 7-parameter transformation. We found points across Australia where we had the GDA 94 coordinates and we had GDA 2020 coordinates. And we developed a 7-parameter transformation. And then if you took those 7 parameters and applied them to the GDA 2020 coordinates and move them back, you get pretty close, but you don't get an exact match. And you don't get an exact match on all your points because there are these localized distortions, whether it be subsidence, earthquakes, or it could be the way that the GDA 94 information was collected and analyzed. So you're dealing with issues in your old datum and errors in your old datum as well. A big part of that, of what caused it in Australia, was that as we went through this process of developing GDA 94, they held fixed in the adjustments to create GDA 94, they held fixed every set of data on top of it. So we went through ITRF 1992, and that was several hundred points in the adjustment. And then we had the Australian Fiducial Network, which was our next level of high quality marks in Australia. That was 8 points. And to move from the AFN down to the ANN, they held fixed the AFN. So holding it fixed with zero uncertainty causes all your movements. If we're talking about our baselines and our GNSS coordinates from yesterday, it's very rigid and you're not allowing for any movement in the way that you're propagating the coordinates down through the adjustments. So by the time that we got to the more than 100,000 points at the bottom, because of this issue of holding everything fixed from the one above, you're introducing distortions and biases. So the way we did it with Dynadjust, as I explained yesterday, is you're putting in constraint, but that constraint comes in within uncertainties. You don't fix it as having zero uncertainty. You've got to have a little bit of wiggle room in there so that all the coordinates can move around a bit. I'm sure they knew this for GDA 94. The problem was they didn't have the software and they didn't have the computing power to be able to handle all of that data set. So they did one step and then held that fixed, and then they took on the next set of data and the next set of data. So it was just a matter of knowing what computational power we had at the time. That was a restriction that we had. It also meant that for most users of the datum, it was fine. GDA 94 was fine when we computed it, but users want more accurate data now. So the data that we use can only be as accurate as the datum. So we need to make sure we have the datum as accurate as possible. And this is what it looks like. If you take out that 7 centimeters of plate motion, so if you have your plate motion and you almost wind it back to GDA 94, you'll see that you're getting all these localized movements that are still happening, local distortions. As I said, it could be subsidence, it could be earthquakes that are causing these localized effects, but it's also largely due to the way that GDA 94 was realized and holding those adjustments fixed in each subsequent level. So you end up with these biases and distortions all throughout your coordinate set. So how can we fix that? This is what that sort of distortion looks at a continental scale. It's not smooth. You can see only in Queensland is it smooth. And it's not because Queensland was perfect in the northeast of Australia, but they took a different approach. They had gone through and recomputed and readjusted coordinates over time. So between GDA 1994 and GDA 2020, they'd be continually removing a lot of these coordinates and adjusting their coordinate set and updating the coordinates and sharing those coordinates with users. But all the other states and territories, they didn't change things since 1994 when it got implemented. So they had more distortions and biases that they needed to remove. So this is what it looks like when you're trying to compute this deformation model. So you can see here those green arrows. The green represents that plate motion, that 7 centimeters a year. And you can't read the numbers there, but that green line, each of those green lines is about 1.5 meters of movement that is caused by the plate motion. But then if you take that out and you look at what's left, you can see the red arrows. And in some cases, they're moving in the same direction, and in other cases, they're moving in different directions. So what you do is you create a grid, as you can see on the far right-hand side, and for each dot on that grid, you estimate what that remaining bias or distortion is at that point. So you can use a mathematical process based on the points around you. to interpolate what that movement might be at each of those grid nodes. So you end up creating like a deformation grid across your country using the remaining components. Now, the process I was explaining to the team yesterday when we were talking over lunch, the process to go through this, it's quite challenging and quite complicated. So you would only go down this path if you felt like the accuracy that you need is really there, and your users are saying, if you just take out the plate motion, it's not going to be enough. I still can't do what I want to do. If that's the case, then you would go down the path of doing something like this deformation grid. But you wouldn't go down the path of doing it unless you really had to, because there's a lot of time and effort that is required. Here's an example from New Zealand where it definitely is required. So they have a good use case. They have deformation models to estimate the movement of the Earth's crust, including the tectonic movements from fault lines and earthquakes. And so they have the New Zealand geodetic datum in 2000, and it's defined through a relationship with ITRF via a deformation model. So a user collects information in real time and then applies a model within New Zealand to make sure that their coordinates are the most up to date. And part of that model is a deformation model. And they have two ways of doing it. I'm not going to go through the details, but the descriptions are in here for your information. They have something called a reverse patch and they have a forward patch. And the reason for that is because the reverse patch allows people to correct coordinates from the past and account for deformation that's occurred since a specific time. Whereas the forward patch projects coordinates into the future or corrects them from to the present to reflect the ongoing deformation. So some people want to know exactly where the coordinate set is now, and other people want to know where was that coordinate at a different point in time. So again, the one thing New Zealand has done really well, and we modeled ourselves on from Australia, is the way that they had engaged with stakeholders. Before they started doing anything technical, they knew exactly what their stakeholders needed. And because of that, they developed alternative approaches that work well together, but they have different user requirements. Some needed to know coordinates from the past, others needed to know where coordinates were now or into the future. They did the communication process really well. Here's some information where you can understand this a bit better. So I'll start with the one on the right-hand side, and that's called the Australian Geospatial Reference System Compendium. So essentially everything that we're covering this week, all the different modules we're covering this week, the way that we did that in Australia is documented in that manual, in that compendium. And there's a link to that in your roadmap at various points. It directs you to different chapters where if you want to do this in your country, have a look at an example from Australia where they did it in chapter 9 or chapter 7, whatever it might be. So that's a good reference guide if you think, I don't know what this means in my roadmap. You can go and see how it was implemented somewhere else. On the left-hand side, this is some Python code. So if you're looking to try and do some of the mathematics using the models, a lot of this has been written in Python code, and this is available on GitHub as well. And again, there's references to this in your roadmap guide, but it avoids you having to develop the software, and hopefully you won't find any errors, but it's being quality checked as well. So it means that you have a reference guide to do some of these calculations if you need it. This is sort of a front end. This is the way that a user would interact with these transformation services. So there's a range of different websites. The one on the left is an Australian one that we developed, and the one on the right is a European one, where users can go and input their data in one datum, and then it gets uploaded to a cloud server. The transformations are applied for them, and then they get an email to say you can go and download your data set from here. So something, again, as the experts, what you can do is develop how you do this and then put it in a system like this so the users can just get it done for free, or it could be a paid service depending on what you want to do in your country, but you're taking a lot of the complexity out of it for the user. They can just upload things like GIS files, and all the transformations will be applied using the information that you have fed into the system. This is a wonderful diagram that kept me up for many, many hours as I was trying to work out, if we come back to our friend from yesterday, standards. We had to work out how to go from, sorry, it still gives me shivers when I look at this diagram. If you're trying to work out how to go from your old datum, which is in the top left, which is GDA 94, through to the new datum, GDA 2020, and then how that interacts with things like ITRF, WGS 84, and there's different types of WGS 84 within EPSG. The way that WGS 84 is realized in standards makes it extremely complicated for the user. Many people don't realize that WGS 84 is a time-dependent reference frame. Coordinates change with time. In Australia, that's 7 centimeters a year. That can create massive problems for users. It'll be less for you, but it's smaller, sometimes makes it even more confusing for users. If you've got a few 2 or 3 centimeters per year, that's sometimes more confusing for users because they don't know why the coordinates keep changing. They might have different data sets captured 20 or 30 years apart, and you're seeing these discrepancies between the datums. And the software really struggles to handle these deformations. So we're working with Esri, and I take my hat off to them. They're doing a great job to try and come up with ways to make this clearer and more accurate for the user. But if you're starting to see these differences between coordinate sets or your data sets in Esri, it could be due to the fact that you don't know if you're working in WGS84 G1762, and I'm sure everyone knows what that is, versus WGS84 generic. We had big problems with this with Australia, and through talking with the team at Esri, we realized that the way that it's implemented within a lot of software is that it's a low accuracy, they call it a low accuracy ensemble datum. And ensemble means that it's a collection of all the different WGS84 realizations. So it's very unclear if you apply a transformation from your country to WGS84, which of these paths it's actually following and how accurate it is. As opposed to ITRF, if you transform to ITRF, you will know exactly what you're getting and it'll be as precise as you can get it. And that's why I keep recommending to people to be working within ITRF and not within WGS84. So that's there for your reference, and you can see there's accuracy statements in there for each one of them. The accuracy statement for the one on the far right-hand side to get to ITRF, that can be done at the millimeter level. Whereas if you look at the WGS84 generic, if we put that into software using the EPSG codes, it comes out with accuracy of 3 meters. Now, what would you rather, a millimeter accurate datum for your country or a 3 meter accurate datum? I know what I would be choosing. Okay, so I'm going to stop there. In the next session, just after this, I'm happy to take a few questions, but before morning tea, I'm going to take you through an example of how you develop transformation parameters and show you the results of going through one of the processes that I found a record of from Fiji. But I'm happy to stop here as I'm swapping over. If anyone's got any questions about this, I'm happy to take it. Thank you. Aslam, thanks.
Thank you very much, Nick, for that presentation. My question relates to one of your first slides where you were trying to show the development of transformation parameters between old system and new system. I think the reality is that in our continent, we don't have ellipsoidal coordinates for the old data set, the old system. And technically, I was always asking myself how to, what is the implications of using null heights, in other words, zero heights? So for example, you can't put in, we might have orthometric heights of various natures, and we don't know the relationship. From the old system, we might only have orthometric heights, and also not well defined as well. So we have old horizontal coordinates and no old ellipsoidal coordinates. So when we move from lat long and heights, what heights do we use? And if we use a null height, what is the impact on the transformation parameter when you go when you try to determine transformation parameter, it's a technical issue which I've been struggling with. I'm not maybe asking for a response now, but I think a lot of us in this room, if not all of us in this room, will be faced with that challenge. And I think it'll be good that at some stage we get some guidance on that matter. Thank you.
Yeah, it's a great point. Thank you. I talked to a few people about this yesterday. They said they had some trig heights where they might have latitude and longitude, but they may not have the old height above whatever spheroid or ellipsoid it was. In most cases, it's the Clark 1880. If that's the case, it's very difficult to develop transformation parameters. You're very limited in terms of the accuracy of how you can do it. There are alternative methods like a block shift method that you can use that are out there that's essentially moving the coordinates in it's almost a two-dimensional transformation just of the horizontal coordinates. But my understanding is that they're not as precise as the 3D one, obviously. So I think that's on my to-do list. I want to go and find some examples of where that's been done in other places and maybe talk to you about how accurate it is. And then it's going to be a decision if, let's say it's only accurate to 5 meters instead of less than 1 meter. If you had 3D coordinates, you may want to decide, is it even worth going through that process? Or do you just want to go and re-observe the information that you had in that old system? Do you want to re-observe it with GPS now and then bring that into your database? So it's really going to depend on what accuracy you need and the importance of that old data set. Does that make sense?
Nick, sorry, I just need to respond to that. The reality is, unlike, for example, the Australian datum where you had an old geocentric datum, you want to go to a newer geocentric datum where you could have had that. There was no, and there will be no ellipsoidal heights on the non-geocentric Cape datums or those like Clark and things like that, because the technique wasn't available. So I think what I was trying to also ask was, if you put in zero ellipsoidal height for your source, what would the impact be on the computation? So it's a technical issue, and again, I'm not expecting a response now, but we all are thinking about this. Thank you.
Yeah, sorry, I neglected to answer that bit. The short answer is you can't do it. You can't develop transformation parameters without the height. They can be, even if you estimate them, you're really going to struggle to come up with anything that's worthwhile, is my understanding. Yes.
Yeah, thank you, Nick. Very excellent presentation. I just want to share the experience we had in Nigeria, exactly what Nick painted. When we did the computation, we discovered that the variation we have on the planimetry, tolerable. But when we get to the height, at the validation point, there were problems. And what was the problem? The problem was the issue of the original autometric height that were acquired for the country. Because you need those autometric height to be converted to ellipsoidal height in the local datum before you can compare and pair it with the ellipsoidal height derived from a GPS, so that you can achieve result that is valid. So when we did that, I think we used about 56 for this first, and then we reserved some point for validation. At the point of completion, we discovered the height problem. So I decided to ask the mapping agency, how did you collect this data set? How were they collected at the beginning? And the answers were, different. They claim the old method was triangulation, and then you use a trig method, and then geodetic leveling, from the datum in Lagos, and then it was a combination of orange and apple, or a mixture of salt and pepper. So at the end of the day, diluted the results. So what Nick said is very valid. The moment you don't have 3D values or coordinates in the two datum, there's no way you'll be able to compute. But what you can do, if you have minimal data, maybe if it is 10, no matter how small, you will have to have a value, a first solution from where you can do a validation, go to the field, and then check. I think that's what we did for Nigeria. We'll call it version 1, 2, 3, 4. And the next one we're going to do, we believe is going to be better. I think the difference we had was a 1-point-something meter for some of the stations that we suspected were so erroneous. And we believe that 1 meter is enough problem in geodesy. Of course, we know that in geodesy, there's no perfect solution. But however, we try to approximate. So one is said is valid. There's no way you can compute transformation parameter if you don't have coordinates in the 2D datum that you can rely upon. Thank you.
Yes, thank you.
Merci beaucoup. Thank you very much, Nick, for the presentation. Indeed, to come back to what my speakers have said, we have a specific situation in Africa, because in these situations, it is very easy to do transformations. But what you have in our countries is that we have old networks. What I've understood up till now, there are some countries that still have the bidimensional systems that they had in the past. So the main problem is availability of datum. We've said in your presentation that we cannot hope to get precise results in the transformation if the system itself is not precise. We cannot expect a precise system. And the challenge we have, we saw it in Senegal with the modernization project, despite the fact that we moved to a three-dimensional system in 2004 in some areas, parts that were still in the old system, 2D. There were land titles that were in the old system, so they were not sorted out. People were struggling to migrate that into the new system. So we had to think through how to determine the transformation parameters. Even if you don't have the height, we can try to do it bidimensionally so that you can do a transposition. So we should have data, and the problem on the ground is that we have enough points to do the calculations. Then we don't have metadata on the old system. Without metadata, it is difficult to have an idea how those points were determined and the information that is related to those data. So we can see the kind of precision that we are looking at when we do the transformation. So those are two major problems that we have often in Africa. So the idea of the grid that you've shown, it can apply in our context. That means sometimes we have heterogeneous systems. They're not homogeneous. They were not put in place by a triangulation system. So in that regard, we could have heterogeneity on different points. And in that regard, having a transformation system with a grid with different transformations that can change could also be a solution. So this is a reality that we have, and we could be able to have more of that experience. Those are the challenges that we could be running into. Thank you.
Yeah, thank you. I'm pleased to hear that you think it might be a good solution for you. I've heard this solution has been used in other countries where they see that kind of deformation and they have those problems with the data sets you're talking about, particularly if there's a cadastral reason for this. If it's about property management and property ownership, that's a good reason to be developing something like this, because you'll get support from your government and from your minister to get the money to do that kind of project, because it's worthwhile for the country. So I'm glad that was helpful, and I'm happy to share some more information about the process you can go through to do that. Thank you.
Okay, thank you. The suggestion I have is, I don't know, maybe we can think this together. The way we can possibly generate the autometric height so that we'll be able to resolve this problem for countries that have not done it before, they have not acquired them, we can try this. It's like walking from the answer to the problem. We can have our GPS campaigns that we have, collect them in a pool, have your data registry, then see how we can do GPS leveling using EGM 2008. After you've been able to use the first or second or third polynomial, if you're able to realize any result from the GPS leveling, then you go back to the field to validate each of those. Maybe you can validate up to 50 or 100 using geodetic leveling technique. That is the only way we can reverse the hand of the clock. That's just a suggestion. Thank you.
Hello, everyone. Frankly, I don't have this experience to transform to transform the coordinates to datum, and frankly, in our studies of deformation, we don't really care about this transformation of the datum, and we calculate the deformation with respect to a stable plate. For example, what we see in the rift of the Western Africa is we can see it with respect to Africa. So maybe this is the distortion, what you call. And for earthquakes, we have also another issue. We have interseismic deformation and coseismic deformation. So the interseismic is a velocity in millimeter per year, and the coseismic deformation is a displacement in meters. Or so there are many parameters. I think which one to choose to include them in the transformations. For local studies, we consider that we are in a plate, and so this is the residual from ITRF maybe, and we don't have we don't have the link with the datum, local datum. It's everything is calculated in a global reference frame, and how to move to this. And when we have an earthquake, we have a displacement, and how to do this when we choose velocities or displacements. Thank you.
Thank you very much for the presentations. I have 3 questions, and I will be fast about it. Number 1, I observed there is no consistencies between the ITRF between 1994 and 2008. But from 2008 up to date, there is consistencies of 6 years. As the international community in Geodesy agreed to 6 years computation of ITRF now, or there could still be inconsistencies moving forward? That's number 1. Number 2, what is...
Hang on, can I stop you? Because I can't remember questions, so I'm going to answer them as you go, okay? There is no specific time frame. As I mentioned before, the community decides when they think they have enough new data to make a significant change for the user community. That's when they adopt a new reference frame. And there has been, it's plateaued in terms of the accuracy at the moment. That's because, I think mostly because we don't have enough VLBI and SLR stations spread out around the world to make a significant difference for a new one. That's question 1.
Thank you. Number 2, what is the relationship between the number of points to realize any ITRF stroke transformation with regards to the size of a country? What is the percentage? For example, now you consider like Australia example. You started with a 21 point, if I'm right, and you've got to over 100,000 of points now. So what is the relationship? Like you can know your landmass and say, okay, for Nigeria, our size is so square kilometer, and the minimum we need to have a good transformation or realization of our datum will be so number of points. Is there a relationship as already agreed?
I would not think about don't think about it as a specific number of points. Think about it as a quality. So we went through a process in 2012 where we did an update, and at that point we decided we have 21 points that were of sufficient quality that we can say we are going to trust these points. And then in 2017, we had 109. So it was about where that bar was, and we set a quality bar, and we said any site that is above that quality bar in terms of accuracy, reliability, and stability, we are going to include those points in datum development. That's the best way to do it.
What is the common physical or practical effect of movement, earth movement, or deformation that one can use as an example for policymakers in each country? If you remember when we started on Monday, we need to tell them that, look, if you don't do this, this will happen. In practical sense, you will die. If you don't do this, you are going to die next year. And they all get scared and then they do it. So if we have common practical experience that, look, this screen was here last year, but now this year is here. And then if you don't take care, your house will be in airports by next year, and then they can act accordingly.
I've never used death as an example to convince a minister, but I think it might work. That could work if you have a good reason. The example, I'll be brief. The example you use depends on the country and it depends on the minister. So in Australia, we talked about mining and we talked about agriculture and we talked about aviation safety in remote and regional parts of Australia. And when I talked to the specific minister, I talked to him about having his kids in the back of his car screaming that they wanted a Happy Meal from McDonald's, and the blue dot on his map wasn't working, so he couldn't navigate to the nearest McDonald's in his car. Then he understood, that blue dot, that depends on GPS, that depends on Geodesy. So he was thinking about his community, who are a big, strong farming community, and the agriculture sector and the benefits it provides them. But there was this personal message in his head about the blue dot and being able to get to McDonald's with screaming kids in the back of his car. So you need to personalize the message for the person and for the country. And you need to give that a lot of thought. That's part of part one in your roadmap. Give that a lot of thought. Sorry, how many more have we got? We've got 17 more hands. I know you had your hand up first, so I'll come back here and then I'll take 2 more.
Yeah.
That's all, sorry.
Yeah, thank you very much, Nick. I've really enjoyed your presentation. And from what other members have talked so far, I could realize that in Africa, what we are lacking is how to determine the geoid ellipsoid separation with respect to our local ellipsoids. If you're able to do that, then we could easily add that one to the autometric height. Then we can get the ellipsoidal height. So now the point is, how do we determine the geoid ellipsoid separation with respect to our local ellipsoids? Thank you.
So if I can hold on that one for now, because we have a presentation after the morning tea break on geoid model development and height datums. So we can talk about that then. All right, I'm going to be very UN here. I'm going to take 1 female and 1 male, okay? Edna first.
Okay, thank you. About the point about controls that are used in creating these transformation models, the main thing you talked about accuracy, but in the local datums, in the datums we have, maybe in Uganda, the local datum we have, these controls were established in different phases. First, 0 order, first, second. And I think doing transformation, using 0 order would be more better to use because the accuracy is better. But most of these controls were actually destroyed. So if you find like maybe first or 0 order, you have like 1 point, and maybe you have more first, and now you have the second, which accuracy is not the same. Now, we have been having debates whether to add a certain category of controls from a certain order into the transformation to improve them. But again, knowing the accuracy is not the same like the others. So is that going to, in your view, is that making it better or it could actually make it worse?
The first thing I think of is that's a fun problem to have, because you get to play with the data. I would do a test where you use your 0 order and first order, And then I would do another test where I use your 0 order, first order, second order, and then maybe all go down to third order. But with your first, second, and third order, I would increase the uncertainties in the, we talked about weighting yesterday. So how much can I rely on this data set? And I would give a bigger uncertainties to your 1, 2, and 3 levels as you go out, increase the uncertainties on the data that's going into that adjustment. And then, as Professor mentioned before, do some validation, capture some other points, and test with some independent to determine which one gave you the better result. Did having more data going in at the start and weighting the data help, or did having less data going in that you could really trust only using that data set and then validate it using some independent test points? So it's a kind of a complex process, but I'm happy to work with you on a plan how you could do that. It's almost like an honors student project or a university project where you could get someone to test all the different options. But that would be a good way. We try multiple ways of doing it using a range of different weighting on your input data. And Bruno, thanks.
Yes, thank you, Nick, for the presentation. About the effect of the heights, there is a model that was proposed in 1999 by the late Professor Wills Featherstone from Curtin University. And I've shared a paper on our page. I see in Ghana, Tayao tried to do the same, and that about 0.5 in terms of root mean square. So I think as Africans, we can also test to see, and that model that was proposed by the two professors who I have trust in over Africa, and we see, can we do the same and see? The other thing, as Nick made a presentation on the deformation, I just want to know, in Australia, did you try to incorporate ocean loading model while doing the computation of the deformation, or it's something out of scope while doing the deformation model? Thank you very much.
The ocean loading is only applied when you're doing the original GNSS analysis. So what we're doing, we're down at the coordinate level. So that's an application source. So there's no ocean loading that's done as part of that. All right, I want to move on to the next part to show you an example of creating transformation parameters. But before I do, I want to invite Israel to give us an example of his, we were having a talk beforehand. I found a great paper. It's been done by the academic community in Nigeria, how they developed transformation parameters in 2019. And I wanted to know, has it been implemented? And I'm also keen to know, how is it being, although it may not be being used by everybody, how is it being used by the community in Nigeria? So if you can give us a short example, that would be great. Thank you.
Thank you so much. So in Nigeria, some things work theoretically and then practically it's not operating. So like I said, or like I told Nick while we're discussing, sometimes it's the technical component can be faster than the first 5 phases that we were considering looking at the roadmap. So for me in Nigeria, the idea is that whichever one works faster, let us keep doing it. And then if we can now be able to catch up later, then maybe that will be fine. Maybe I should add this to what I want to say. While you were talking about the challenges of EPSG, sorry, of WGS84 rather, and I was looking at the impact on the user. You know, in Australia, you have a platform where the impact of these changing locations can be easily cited and the minister will understand. Unfortunately, in Africa, the widely available one is the Google Earth. That's where most persons, most users who are not geodesists go to as a point of reference. And most persons don't know that this thing is not static. It's actually time dependent. So is it possible to have a platform, maybe network with the computer scientists, and then maybe the remote sensing experts, and then they come together and build a platform where it can be easier also for the users to see this impact, because I really believe that will be a very good collaboration, and then that will also be something that would impact and help us to show our governments that, okay, you know this platform, and then this is the impact of these things. Thank you.
Thank you. It's the old communications method of show, don't tell. If you can show the problem, then you don't have to talk about it so much. So yeah, thank you for that.